The night sky appears timeless to the unaided eye. Generations of people have looked up at the stars and believed they were eternal, shining without beginning and without end. Yet modern astronomy has revealed that time is woven into the cosmos itself. Every star, every galaxy, and even the universe, as a whole, carries within it a record of age. The universe is not timeless. It has a past, it has a present, and it will have a future. If we listen carefully enough, we can learn how long the story has been unfolding. When scientists set out to measure cosmic time, they turn to natural clocks that tick on scales far beyond human lifespans. Radioactive decay is one such clock. On Earth, geologists use the decay of uranium into lead or potassium into argon to determine the ages of rocks. These methods rely on the fact that unstable elements change into more stable forms at constant and predictable rates. If you know how much of the original element remains and how much has turned into its daughter product, you can calculate how much time has passed. This principle extends to the stars as well. Heavy elements forged in the cores of exploding stars also undergo radioactive decay, providing clocks that tick for billions of years. Another clock is found in the lives of stars themselves. A star is powered by the fusion of hydrogen into helium in its core. This process is steady and predictable, and the total supply of hydrogen in a star's core determines how long it will shine. A star like our Sun will live for about 10 billion years, while a star many times more massive will exhaust its fuel in only a few million years. Conversely, a star much smaller than the Sun will burn its fuel slowly and could shine for trillions of years. By observing the brightness, color, and chemical composition of a star, astronomers can place it on a timeline of birth, middle age, and eventual death. These stellar life cycles serve as another set of natural timekeepers. There is also the largest clock of all, the expansion of the universe itself. In the early 20th century, astronomer Edwin Hubble demonstrated that galaxies are receding from us, and the farther away they are, the faster they recede. This discovery led to the understanding that the universe is expanding. If it is expanding now, it must have been smaller in the past. By measuring the rate of expansion, known as the Hubble constant, astronomers can estimate how long the universe has been stretching since its beginning. Just as rewinding a movie leads you back to the opening scene, running the expansion backward leads to the moment when the universe was condensed into a state of extraordinary density and heat. For decades, scientists debated the age of the universe using these different clocks. Stellar ages gave one set of answers, while expansion rates gave another. The question demanded precision, because if the clocks disagreed, it would mean either that our physics was incomplete or that our observations were flawed. The breakthrough came from the study of the cosmic microwave background. This faint glow of radiation fills all of space and is the leftover heat from the hot early universe, released when matter and light first separated about 380,000 years after the Big Bang. Sensitive instruments aboard satellites, such as the Wilkinson Microwave Anisotropy Probe and later the Planck spacecraft, map this ancient light in exquisite detail. The ripples and patterns in the cosmic microwave background encode the density, composition, and expansion history of the universe. By analyzing this fossil light, cosmologists arrived at an age of about 13.8 billion years. This number has become the benchmark, the most precise determination of the universe's age ever achieved. It tells us that everything we see, from the faintest star in the Milky Way to the most distant galaxy captured by the James Webb Space Telescope, fits within a timeline that stretches back nearly 14 billion years. The cosmic microwave background is therefore a master clock, against which all other measures must be tested. This cosmic clock does more than assign a number. It sets boundaries for our understanding of nature. If the universe is 13.8 billion years old, no star, no cluster, no galaxy can legitimately be older. It provides a framework that must be consistent with every other observation in astronomy. This is why age determinations are not mere curiosities. They are essential tests of our knowledge of physics, from nuclear reactions inside stars to the geometry of space itself. A contradiction between the cosmic clock and stellar clocks would challenge the very foundations of cosmology. Yet this is exactly the puzzle that astronomers have faced. In some cases, stars have appeared to be older than the universe itself. This is not possible in reality, but the fact that measurements come so close to breaking the boundary shows how delicate the science of cosmic timekeeping can be. Even tiny adjustments in the assumed physics of a star can shift its estimated age by billions of years. The clocks of the cosmos tick with both precision and uncertainty. As we move forward, we will see how these stellar timepieces are built, how they sometimes seem to run faster than the cosmic clock, and how astronomers resolve the tension. The night sky is not only a spectacle of beauty, it is also a record of time, written in starlight. And so the story of cosmic time begins with the master clock of the universe itself. But the tale does not end there. For even with this foundation in place, some stars appear to challenge the very clock of the cosmos. The quest to measure time on cosmic scales did not emerge fully formed. It was built step by step as human beings pushed their instruments, their mathematics, and their imaginations further into the depths of the sky. After the determination of the universe's age through the cosmic microwave background, attention turned to whether other cosmic clocks told the same story. Agreement would mean confidence. Disagreement would mean cracks in our understanding of physics. One of the most important tests came from the study of globular clusters. These are dense spheres of stars bound together by gravity, hanging like ancient lanterns in the halo of the Milky Way. Each cluster contains hundreds of thousands of stars, all born at roughly the same time, making them natural laboratories for stellar evolution. When astronomers plot the brightness and color of stars in these clusters, they find a clear curve that traces their life stages. At a certain point, the curve bends sharply, marking where the most massive stars have already burned through their fuel and left the main sequence. The position of this turn-off point acts as a stopwatch, telling us how long the cluster has been shining. In the middle of the 20th century, calculations of cluster ages often suggested numbers greater than the age of the universe implied by expansion rates at that time. This was a source of tension. Either the universe was older than astronomers thought, or the models of stellar structure were incomplete. Improvements in both cosmology and stellar physics eventually brought the estimates into harmony. By including more accurate treatments of how atoms absorb light inside stellar interiors, and by recognizing the effects of element diffusion, the ages of the oldest globular clusters were revised downward. Instead of 15 or 16 billion years, the consensus shifted toward about 13 billion years, compatible with the cosmic microwave background. White dwarf stars provided another independent check. These are the corpses of stars like the Sun, left behind after they have shed their outer layers. Once a white dwarf is formed, it no longer produces energy. It simply cools over time like an ember fading in the night. By measuring the faintest and coolest white dwarfs in a cluster, astronomers can determine how long they have been cooling, and therefore how old the cluster must be. White dwarf cooling ages also point to values near 13 billion years, again in harmony with the overall cosmic clock. Despite these successes, there remained individual stars whose estimated ages continued to push at the boundaries. Among them was the so-called Methuselah star, catalogued as HD 140283. This star drew attention because its calculated age once appeared to exceed 14 billion years, older than the universe itself. Such an outcome cannot be true, yet it was not a mistake easily dismissed. The observations were precise, and the methods followed the best physics available at the time. The only way forward was to refine the models even further, adjusting opacities, nuclear reaction rates, and the mixing of elements inside the star. Over time, these refinements reduced the estimated age to about 13.7 billion years, with an uncertainty of 700 million years. In other words, the star was not truly older than the universe, but it was old enough to press right up against the limit. Cases like this demonstrate the power and fragility of cosmic timekeeping. A slight change in the assumed distance to a star, a small adjustment to how efficiently convection transports energy within its layers, or a minor revision to the rate at which elements like oxygen absorb light can shift an age estimate by hundreds of millions of years. When dealing with timescales comparable to the age of the universe itself, such uncertainties matter profoundly. The drive to reconcile all these clocks has become one of the defining challenges of modern astrophysics. It is not enough to have one measure of the universe's age. To trust the cosmic timeline, astronomers demand convergence from multiple directions, from radioactive decay in stellar atmospheres, from the cooling of white dwarfs, from the turn-off points of globular clusters, and from the ancient fossil light of the cosmic microwave background. Only when all these independent methods point to the same era can we be confident that our story of the universe's past is correct. Still, a shadow of doubt remains. What if some systematic error lurks within the physics of stars that we do not yet understand? What if dark matter or unknown particles subtly alter stellar life cycles? What if the expansion history of the universe contains surprises we have not yet uncovered? Each apparent contradiction becomes a probe, forcing scientists to sharpen their tools and expand their theories. The closeness of the agreement between the ages of stars and the age of the universe is both reassuring and unsettling. Reassuring because it shows our theories hold together across scales, from the nuclear to the cosmic. Unsettling because the margin for error is so narrow that even the smallest misstep could tip the balance. As this narrative unfolds, we will explore the methods by which astronomers date stars with ever greater precision. From the vibrations that ripple through a star's surface to the faint signatures of radioactive elements in their spectra, each approach adds another layer of evidence. It is a pursuit not only of chronology, but of truth, for the ages of stars carry within them the story of the universe's beginning. The cosmic microwave background provides a master clock. Globular clusters and white dwarfs provide secondary clocks. Individual stars like HD 140283 test the very limits of precision. Together they form a network of timekeepers, ticking across billions of years, converging on a universe that is 13.8 billion years old. Yet, as we peer closer, we will see how fragile this harmony is, and how a single miscalculated star can appear to challenge the entire timeline of the cosmos. The universe may have a master clock, but the test of that clock lies in the ticking of countless stars scattered across the sky. And some of those stars, as we shall see, seem determined to test the patience of time itself. The pursuit of cosmic time is not only about numbers written in charts, it is about building a coherent story of the universe itself. When astronomers measure the age of stars, clusters, and galaxies, they are testing whether the universe is consistent with itself. A contradiction would not just be an error of arithmetic. It would mean that something fundamental about nature is missing from our understanding. That is why scientists treat the age of the universe with such care. It is not simply a curiosity, but a cornerstone. To appreciate the depth of this task, imagine trying to measure a single lifetime while the clock you use has never been calibrated. For most of human history, people could only judge time by the rising and setting of the sun, by the changing of seasons, or by the growth of children. These were crude, but practical clocks. With the development of mechanical timepieces, accuracy improved. Eventually, atomic clocks based on the vibrations of cesium atoms gave us precision down to billionths of a second. In the same way, cosmology has moved from rough estimates to precision measurements. The cosmic microwave background functions as a kind of atomic clock for the universe, a benchmark against which all other measures must be compared. Yet there is always tension between local and global scales. Stars live in their own environments, subject to processes of nuclear fusion, convection, and chemical mixing. They do not know about the expansion of the universe. Their ages are derived from physics that operates within their cores. The universe as a whole, on the other hand, evolves through cosmic expansion, dark energy, and dark matter. To demand that these two completely different kinds of clocks agree with each other is to test whether our knowledge of physics is truly universal. If the ages of stars consistently exceeded the age of the universe, it would suggest that one of our most basic assumptions is wrong. For now, the evidence points toward agreement, though it is an agreement balanced on a knife edge. The Planck satellite's analysis of the cosmic microwave background gives us 13.8 billion years. The oldest globular clusters come in just under that, around 13 billion. White dwarf cooling supports similar values. Even the Methuselah star, after revisions, nestles within the uncertainty limits. The harmony is delicate but real. However, the very closeness of this agreement raises questions. Why do the oldest stars and clusters lie so near to the maximum possible age? Is this coincidence, or does it hint at something deeper in the way matter and energy evolved after the Big Bang? Could small changes in the assumed physics of the early universe shift the cosmic clock by a few 100 million years? These are not idle speculations. They drive active research, with astronomers cross-checking every method against every other to uncover hidden biases. The cosmic story is therefore not one of absolute certainty, but of converging lines of evidence. Each new instrument, each new measurement, narrows the error bars and strengthens the case. Where once the ages of stars and the age of the universe seemed irreconcilable, today they stand in close alignment. But the memory of past contradictions lingers, reminding scientists to remain cautious. This caution is not a weakness. It is the strength of science itself. By questioning, by testing, by refusing to accept contradiction without explanation, astronomers have refined their understanding of both stars and the cosmos. The story of time is not only written in the light of galaxies billions of light-years away, but also in the faint flicker of a single star just beyond our solar neighborhood. Each measurement is a vote of confidence in our theories, or a challenge that demands a better one. As the 21st century unfolds, new telescopes and satellites continue to sharpen this picture. The Gaia spacecraft measures stellar distances with extraordinary precision, reducing one of the key uncertainties in age estimates. The James Webb Space Telescope peers into the faintest and earliest galaxies, giving new benchmarks for when stars and clusters first formed. Each new observation is like the tick of a cosmic clock, adding rhythm to the narrative of the universe. The story of time in the cosmos is therefore not finished. It is a living dialogue between theory and observation, between the immense scale of the universe and the local detail of individual stars. It is a story that shows us how fragile knowledge can be, yet also how powerful, careful measurement is in revealing truth. The universe has a clock, and for the moment it reads 13.8 billion years. Against this backdrop, the stars shine as witnesses. Most comply with the limit, but a few seem to strain against it. Their ages appear to reach out toward eternity, challenging the very boundaries of time itself. And so we come to the mystery that drives this book forward. How is it that some stars seem to be older than the universe that contains them? What does this tell us about the physics of stars, the structure of the cosmos, and the limits of our understanding? The paradox is not that the stars truly outlive the universe, but that our measurements bring them so close to doing so. The answers lie in the details of stellar clocks, and in the careful reconciliation of cosmic history with the light of the oldest stars. Yet, some stars appear to challenge the very clock of the cosmos. When astronomers speak of dating stars, they are not invoking romance but physics. To determine when a star was born and how long it has been shining, scientists must probe the processes inside it, processes hidden beneath layers of gas that no telescope can penetrate directly. Unlike tree rings on Earth or archaeological artifacts buried in soil, the evidence of stellar age does not sit waiting to be uncovered. Instead, it must be inferred from models of nuclear fusion, from the way stars shine and vibrate, and from the elements written in their light. The art of stellar dating is a triumph of deduction, grounded in physics that has been tested in laboratories and confirmed across the universe. The first tool is stellar structure itself. A star is not an eternal beacon, but a reactor, powered by the fusion of hydrogen into helium at unimaginable pressures and temperatures. In the core of our sun, each second, about 4 million tons of mass are converted into energy. This process releases light and heat, which slowly work their way outward through the layers of gas before escaping into space. The rate of this fusion depends on the star's mass. A massive star burns furiously, consuming its fuel quickly and dying young. A small star sips fuel slowly, glowing faintly but enduring for trillions of years. By measuring a star's brightness and temperature, astronomers can place it on what is called the Hertzsprung-Russell diagram, a map of stellar life stages. Its position reveals how far along it is in its journey, and therefore how old it is. Clusters of stars provide a particularly clear picture. Because the stars in a cluster are born together, their spread along the Hertzsprung-Russell diagram shows which types of stars have already left the main sequence, the phase where hydrogen fusion dominates. The point where stars begin to peel away is known as the main sequence turnoff, and it acts like the hand of a clock. More massive stars leave the sequence first, so by seeing which stars have departed, astronomers know how many billions of years have passed since the cluster's birth. Isochrone fitting, the technique of overlaying theoretical models on observed data, allows precise age estimates. This method has placed many globular clusters at around 13 billion years, showing they formed shortly after the birth of the universe. Another method comes from radioactive dating within stars themselves, an approach called nucleocosmochronology. Just as geologists on Earth measure the ratios of uranium and lead in rocks, astronomers can analyze the ratios of long-lived radioactive isotopes such as uranium-238 and thorium-232, compared with stable elements like europium. Because these isotopes decay at known rates, the relative amounts act as chronometers, indicating how long the star's heavy elements have been in existence. These measurements require highly precise spectra, teasing out faint absorption lines from the star's light. Although challenging, this method has confirmed ages of more than 13 billion years for certain ancient stars, offering direct radioactive evidence that they were born in the earliest epochs of the Milky Way. Yet another clock comes from the very vibrations of a star. Just as earthquakes send seismic waves through Earth, a star can resonate with sound waves bouncing through its interior. These vibrations cause tiny changes in brightness, detectable by sensitive instruments. The Kepler and TESS space telescopes have recorded such oscillations in thousands of stars, enabling the science of astroseismology. The frequencies of these oscillations depend on the star's internal density and structure, which change predictably with age. By decoding the music of a star, astronomers can estimate its age with remarkable precision, sometimes within a few percent. Still, every method carries uncertainty. Stellar models depend on inputs such as how atoms absorb light at different energies, how elements mix within turbulent interiors, and how helium settles under gravity over billions of years. Even small errors in these parameters can shift an age estimate by hundreds of millions of years. For a young star, that may not matter much. But for stars near the age of the universe, it can mean the difference between consistency and paradox. The challenge is to refine every assumption until the clocks converge. This is the essence of stellar dating. No single method is sufficient, but taken together, they weave a net of evidence. Each technique has its strengths and weaknesses. Isochrone fitting excels for clusters, but is less certain for single stars. Radioactive chronometers are powerful, but limited by faint signals. Asteroseismology is precise, but requires stars bright and stable enough for detailed monitoring. Where the methods overlap, confidence grows. Where they disagree, astronomers look for hidden complexities, probing deeper into the physics of matter and radiation. The story of how we date the stars is therefore not just about measuring time. It is about confronting the limits of knowledge, balancing precision and uncertainty, and constantly testing the models against observation. It is a story of how humanity has reached beyond the veil of starlight to read the ages of suns that burned long before our world formed. And with these tools, we have found stars that press against the very edges of cosmic time, forcing us to question whether we have understood the universe's clock as well as we thought. Stars do not reveal their ages willingly. They shine, they burn, they evolve, but they do not mark the passage of time in ways that are simple to read. Every method we use to date them is indirect, rooted in our understanding of physics. This reliance is both a strength and a vulnerability. It means that by trusting the universality of natural laws, we can stretch across billions of years. But it also means that if any piece of the physics is slightly misunderstood, our estimates may drift away from truth. Take isochrone fitting as an example. When astronomers compare a cluster's color and brightness distribution to theoretical models, they must assume how energy moves through a star's interior. In reality, that transport is shaped by complex processes. Convection, where hot material rises and cooler material sinks, mixes elements in ways that are not fully captured by simple models. Microscopic diffusion, in which heavier elements slowly settle deeper, while lighter elements float upward, changes the composition of the star over time. Even tiny shifts in how opacities are calculated, meaning how atoms absorb and scatter light, can change a star's apparent brightness at a given age. Each uncertainty feeds into the final answer, so that a cluster estimated to be 13.5 billion years old could in truth be a billion years younger or older. The radioactive clocks face their own difficulties. Measuring uranium or thorium abundances in a star requires detecting absorption lines so faint they nearly vanish into the background noise of the spectrum. Only a handful of stars have been studied with the precision required. Furthermore, the production of these heavy elements depends on rare astrophysical events like neutron star mergers or specific kinds of supernovae. If we do not fully understand how much uranium or thorium was produced at the beginning, then interpreting the ratios today becomes more complicated. Despite these hurdles, nuclear cosmochronology remains one of the few methods that does not rely on stellar models at all. It is a direct measure of time, encoded in the nuclei of atoms themselves. Asteroseismology, though powerful, is still a relatively young field. Its success depends on long, uninterrupted observations of stars, bright enough for tiny variations in light to be recorded. Missions like Kepler provided such data for only a fraction of the sky. TESS continues the effort, but even then, not all stars are suitable candidates. Those that yield exquisite precision. Their oscillations map the density profile of the interior with sensitivity no other method can match. For stars similar to the Sun, this approach has narrowed age estimates to within a few 100 million years, an astonishing feat on cosmic scales. But the limitation is that only certain types of stars can sing loudly enough for us to hear. These different clocks sometimes tell slightly different times. When they converge, as they often do for ancient clusters, and for stars like the Methuselah Candidate, astronomers breathe easier. When they diverge, as sometimes happens, they become opportunities. A mismatch is not just an annoyance, it is a potential window into physics we have overlooked. In the past, such mismatches led to improved opacity tables, better understanding of element diffusion, and more accurate measurements of distances. Disagreement pushes refinement. Agreement confirms progress. It is important to recognize that every estimate comes with error bars. Scientists do not claim that a cluster is exactly 13.2 billion years old. They say it is 13.2, plus or minus a few 100 million years, depending on the uncertainties. The overlap of these uncertainties is what matters most. If the cluster's age overlaps with the universe's age within the margins of error, then consistency is preserved. If the numbers do not overlap, then alarm bells ring. The Methuselah star caused such alarm because its estimated age once seemed outside the boundary. It was later brought back into harmony, not by hand-waving, but by carefully refining the underlying physics. What emerges from all this is a tapestry of techniques, each imperfect on its own, but strong together. Like witnesses in a trial, each star, each cluster, and each method gives testimony about the past. No single testimony can be taken as absolute, but when many testimonies align, the case grows compelling. The universe is 13.8 billion years old, not because one instrument said so, but because every independent line of evidence converges on that story. This careful weaving of methods shows the beauty of astronomy. It is not simply about gazing at stars, but about listening to what their light whispers across immense spans of time. The stars have no intention of telling us how old they are, yet by applying the laws of physics with rigor and imagination, we compel them to speak. And when they speak, they reveal a timeline that stretches back to the earliest epochs, a story that seems to press against the very birth of the cosmos. The effort to date the stars is not just an exercise in cataloging, it is a way of anchoring ourselves within the universe. Our world is young by cosmic standards, only 4.5 billion years old. The Milky Way is far older, with stars that were born before the Earth even existed. To know their ages is to place our own story on the timeline of creation. It is to understand when the first heavy elements formed, when galaxies took shape, and how long stars have been forging the building blocks of life. The reliability of this timeline rests on the strength of our physical laws. Nuclear fusion is not a guess. It is measured in laboratories and confirmed in particle accelerators. The decay rates of uranium and thorium are not estimated. They are constants of nature, unchanged over billions of years. The behavior of sound waves in a vibrating sphere can be modeled with precision, and the match between theory and stellar oscillations confirms our understanding of matter under extreme conditions. These foundations give confidence that our clocks are not illusions. They are genuine reflections of cosmic time. Yet, humility is necessary. The universe has surprised us many times. It was once thought to be eternal and unchanging, until the discovery of its expansion. It was once believed that galaxies were simply nebulae within the Milky Way, until it became clear they were separate islands of stars across vast distances. It was once assumed that the Sun was ordinary, only to find that its stability and environment may be unusually favorable for life. Each time we believed we understood, new observations forced us to refine or rethink. The same may be true for stellar ages. The clocks are strong, but we must always remain alert to the possibility of hidden complexities. This is why the search for consistency matters so deeply. If the oldest stars pressed far beyond the age of the universe, then either the universe is older than we think, or the stars evolved differently than our models predict. Neither option can be ignored. To dismiss a contradiction is to risk building knowledge on sand. To confront it is to strengthen the very foundation of science. The ongoing work of stellar dating is therefore not only about individual stars, but about the structure of the universe itself. The significance extends further. Ancient stars serve as fossils, preserving in their atmospheres the chemical record of the early universe. By dating them, we do more than place them on a timeline. We learn when certain elements appeared, when supernovae enriched the cosmos, and how quickly galaxies formed after the Big Bang. In this way, the clocks of the stars become guides not only to time, but to history. They tell us not only how long ago events occurred, but also what those events were. The most dramatic stories arise when individual stars appear to push against the very edge of cosmic time. Among these, one in particular has captured the imagination of astronomers and the public alike. A solitary star not far from our solar system, catalogued by scientists as HD 140283, came to be known as the Methuselah star for its astonishing apparent age. Its story embodies both the promise and the peril of stellar dating. This star seemed to say, in its light and its spectra, that it was older than the universe itself. The claim could not stand, but it demanded explanation. How could our methods yield such a paradox? The answer, as it turned out, lay not in the failure of physics, but in the precision of the measurements and the refinement of our models. It is a story of how science advances, not by ignoring contradictions, but by embracing them until they yield their secrets. And so, with the tools of isochrone fitting, radioactive dating, and asteroseismology in hand, we are prepared to examine the case of the Methuselah star, the most famous example of a cosmic clock that seemed to outpace the universe itself. The star known as HD 140283 rests quietly in the constellation of Libra. To the naked eye, it is unremarkable, a faint point of light among countless others. Yet this modest star has carried with it a mystery that once shook the foundations of cosmology. For decades, it appeared to defy the ultimate boundary set by the universe itself. By some measurements, it seemed to be older than the cosmos in which it resides. The story of the Methuselah star begins with the rise of precise stellar spectroscopy. In the early 20th century, astronomers began to split starlight into its component colors with increasing accuracy, revealing dark lines caused by atoms absorbing specific wavelengths. These absorption lines act like fingerprints, allowing scientists to measure the chemical composition of stars. In the case of HD 140283, the spectra revealed that it was extremely poor in heavy elements. It contained very little iron compared with the Sun, marking it as an ancient survivor from the earliest generations of stars formed in the Milky Way. Chemical poverty alone was not enough to place it at the dawn of time. What gave the star its reputation was the attempt to calculate its precise age, using parallax measurements from telescopes on Earth and later from the Hubble Space Telescope. Astronomers determined its distance and therefore its absolute brightness. When combined with models of stellar evolution, the brightness and color suggested an age of about 14.5 billion years. That figure exceeded the age of the universe derived from the cosmic microwave background, which stood at 13.8 billion years. If taken at face value, this would mean the star was older than everything around it, older even than the Big Bang itself. Such a result could not be true, but neither could it be ignored. If the star's age were accurate, it would demand a radical rethinking of physics, cosmology, or both. For years, the Methuselah star served as a puzzle, its age estimates hovering at the very edge of possibility. Scientists debated whether the problem lay in the measurements, the models of stellar interiors, or even in the interpretation of cosmological data. The key to resolving the paradox lay in refinement. Age determinations depend on several sensitive factors. One is the rate at which elements inside a star absorb and scatter light, known as opacity. If opacities are slightly underestimated, then the models make stars appear older than they are. Another factor is the efficiency of convection, the turbulent motion that carries energy outward. Changing the assumptions about convection can shift a star's predicted brightness, and therefore its inferred age. Even small revisions to the abundance of oxygen or iron in the star's atmosphere can ripple through the calculations, altering the result by hundreds of millions of years. As astronomers revisited these assumptions with better data, the star's apparent age began to shrink. The launch of the Gaia spacecraft provided the most accurate parallax measurements ever achieved, refining the star's distance. This, in turn, refined its luminosity. With improved input values for opacity, nuclear reaction rates, and chemical abundances, the age estimate settled around 13.7 billion years, with an uncertainty of about 700 million years. In other words, the star could be as young as 13 billion years, or as old as 14.4, but the most likely value was very close to the age of the universe itself. This outcome was both relieving and exhilarating. It meant that the paradox of a star older than the universe dissolved once the uncertainties were properly accounted for. At the same time, it confirmed that HD 140283 is one of the oldest stars ever observed, a relic born in the earliest billion years after the Big Bang. Its light has been traveling through space for the entire history of the Milky Way. Its atoms contain the ashes of the very first supernovae that seeded the galaxy with elements heavier than hydrogen and helium. The Methuselah star remains important because of how close it comes to the cosmic limit. It demonstrates the power of precise measurement and the necessity of constant refinement in astrophysics. It also shows how science grows stronger by confronting apparent contradictions rather than dismissing them. The star did not overturn cosmology, but it forced cosmologists and stellar physicists to tighten their work, to reduce uncertainties, and to prove that the clocks of the cosmos can indeed agree. As we look at this ancient star, shining faintly in the night sky, we see more than just a point of light. We see a witness to nearly the entire history of the universe, a survivor that has carried its memory across more than 13 billion years. It is not older than the cosmos, but it stands close to its beginning, like a sentinel at the edge of time. And if one star can nearly break the cosmic clock, what might entire populations of ancient stars reveal? The Methuselah star's story is not simply about one measurement. It is about a chain of observations stretching across decades, each more precise than the last, and each narrowing the uncertainty around its true age. In the 1950s and 60s, astronomers first recognized HD 140283 as a peculiar object because of its extremely low metallicity. Metals in astronomy mean all elements heavier than helium. Our Sun, born about 4.5 billion years ago, contains a rich mix of metals forged by generations of earlier stars. By contrast, HD 140283 contains less than 1% of the Sun's iron content. This alone placed it among the earliest survivors of the Milky Way. Its chemical fingerprint told a story. In the first few 100 million years after the Big Bang, only hydrogen, helium, and traces of lithium existed. Heavier elements were created later, inside the cores of the first stars, then spread into space by supernovae. The next generation of stars incorporated those new elements, leaving chemical clues to the number of generations that had passed. HD 140283's extreme metal poverty meant it must have formed after only a handful of stellar explosions had seeded the galaxy. Its atmosphere contained the ashes of the very first heavy element production, making it a fossil of cosmic history. Still, the question of its precise age required more than chemistry. It required distance, brightness, and theoretical modeling. In the 1990s, parallax measurements from ground-based observations carried large uncertainties. A small error in distance translates to a large error in luminosity, and therefore in the age derived from stellar models. This is where the Hubble Space Telescope made a crucial contribution. With its sharp vision above Earth's atmosphere, Hubble measured the star's parallax to unprecedented accuracy. The result placed HD 140283 at a distance of about 190 light-years, giving astronomers a far more reliable estimate of its true brightness. Using these values, scientists compared the star's position on the Hertzsprung-Russell diagram with theoretical models. The result was astonishing. It suggested an age of about 14.5 billion years, significantly older than the 13.8 billion-year universe revealed by the cosmic microwave background. The paradox gained widespread attention, not only within scientific journals, but also in the popular press. A star older than the universe seemed to defy logic. Headlines called it a cosmic mystery, a challenge to the Big Bang itself. The paradox was not ignored. Astronomers knew that uncertainties in stellar physics could easily shift the result. The rate at which protons fuse with heavier nuclei in the core, the exact opacity of oxygen and iron in stellar interiors, and the mixing of helium all influence how quickly a star evolves. Each factor carried small margins of error. Added together, they allowed the possibility that the star's true age was younger than 14 billion years. But the central estimate remained troubling. The launch of the Gaia spacecraft transformed the situation. Gaia's mission was to measure the positions and motions of over 1 billion stars in the Milky Way, with parallax accuracy far exceeding anything before. When Gaia released its data on HD 140283, the revised distance was slightly different from Hubble's value. That small shift altered the star's calculated luminosity. Combined with updated stellar physics, including improved opacity tables and nuclear reaction rates, the new analysis reduced the estimated age. Instead of 14.5 billion years, the best estimate became about 13.7 billion years, with uncertainties extending several hundred million years in both directions. This meant that the star could be as young as 13 billion years, comfortably younger than the universe, or as old as 14.4 billion years, brushing against the cosmic ceiling, but not exceeding it. The paradox dissolved, replaced by a picture of a very old star, but not impossibly so. The Methuselah star remained remarkable, but not heretical. It had forced scientists to refine their tools, and in the process, it reinforced the consistency of cosmic time. What is most striking is how sensitive the result was to tiny changes. A shift of a few percent in the assumed opacity of stellar material, or a small revision in the measured distance, altered the age by hundreds of millions of years. In human terms, this is like discovering that a person thought to be 140 years old is in fact 120. Still, astonishingly old, but within the realm of possibility. The Methuselah star teaches us that the boundary between possible and impossible in cosmology can hinge on the smallest details. It is a reminder that precision matters deeply when measuring billions of years. It also shows how science advances not by avoiding contradictions, but by confronting them until they yield. The star is not older than the universe, but it stands close enough to the beginning to illuminate it with rare clarity. It remains a sentinel in the sky, its faint light carrying the memory of nearly the entire age of the cosmos. And as astronomers turned their attention from this single star to the populations of ancient stars bound together in globular clusters, they began to see patterns that confirmed the universe was filled with relics from its earliest days. If one star can nearly outpace the universe, What might thousands of stars in ancient clusters reveal about the dawn of time? The legacy of the Methuselah star reaches beyond its own faint glow. For years it stood as a challenge, a puzzle that demanded astronomers either correct their models or reconsider their understanding of the universe itself. In the end, the resolution did not require abandoning the Big Bang or rewriting the history of cosmology. Instead, it required precision, patience, and the willingness to accept that even the smallest uncertainties can become magnified when stretched across 13 billion years. What the star truly gave us was a lesson in humility. The universe is not careless with its secrets. It demands careful questioning and meticulous refinement. When scientists first announced that HD 140283 might be older than the cosmos, it would have been easy to treat it as an anomaly, to be brushed aside. But anomalies are often where the deepest truths are hidden. By taking the paradox seriously, astronomers refined the values of opacities, nuclear reaction rates, and convection models. They recalibrated distances with Gaia's measurements. Each step brought the science closer to consistency. The paradox was not a mistake, it was a guidepost. The star also highlighted the extraordinary power of modern instruments. Without Hubble's parallax data, the paradox would never have arisen. Without Gaia's refinement, it would never have been resolved. Without improved stellar models, the discrepancy would have lingered. The Methuselah star was not only a test of theory, it was a showcase for the precision of human tools aimed at the heavens. In the public imagination, the idea of a star older than the universe carried a certain poetry. It spoke to the mystery of time itself, to the yearning to understand beginnings and endings. Even after the paradox was resolved, the story remained compelling because it demonstrated how close we stand to the boundaries of knowledge. 13.7 billion years is not a number one can easily picture, yet the Methuselah star makes it tangible. It is a star we can point to in the night sky, faint but real, carrying within it the memory of nearly the entire cosmic story. Astronomers now accept that HD 140283 is among the oldest known stars, but not older than the universe. Its age, consistent within error bars, testifies to the reliability of both stellar physics and cosmology. The very closeness of the match between its age and the universe's age is what makes it so valuable. It shows that our clocks, built from such different foundations, truly converge. The nuclear reactions inside a star, the motions of galaxies across the expanding cosmos, and the fossil light of the cosmic microwave background all point to the same timeline. The Methuselah star is not unique in being ancient, though it is famous. Other stars with similarly low metallicity have also been dated to around 13 billion years. Together they form a population of relics, survivors from the earliest generations of the Milky Way. Studying them is like reading the earliest chapters of a book, where most of the pages are missing. They offer glimpses of what the galaxy was like when it was young, when the first heavy elements were just beginning to spread, and when star formation had only just begun. From this one star, attention naturally shifts to groups of stars, bound together in great swarms. Globular clusters are the natural next stage in the story. Unlike single stars, which carry individual uncertainties, globular clusters provide thousands of examples born at the same time. Their collective light and shared history make them powerful laboratories for cosmic archaeology. The Methuselah star remains a symbol of how science progresses, through contradiction, through refinement, and ultimately, through resolution. Its paradox forced a closer look at both stars and the universe, and in doing so, it strengthened the bridge between stellar astrophysics and cosmology. It stands as a quiet reminder that the boundaries of knowledge are not barriers, but invitations to look deeper. And so, from the solitary endurance of the Methuselah star, we now turn our gaze to the great clusters of ancient suns that surround the Milky Way, vast spheres of light that serve as fossil records of the early universe. If one star can challenge the clock of the cosmos, what story might be told by an entire cluster of them, bound together and shining since nearly the beginning of time? Around the Milky Way, There orbit more than 100 dense swarms of ancient stars, each a glowing city of light, bound by gravity. These are the globular clusters, and they are among the most ancient structures in our galaxy. To look upon one through a telescope is to see hundreds of thousands of suns crowded together so tightly that the stars near the center appear to merge into a single haze. To study them with science is to uncover fossils of cosmic history, for these clusters preserve within them the record of the earliest star formation in the Milky Way. Globular clusters are remarkable for their uniformity. Each one contains stars that were born nearly at the same time, from the same cloud of gas, more than 13 billion years ago. They orbit far above and below the plane of the galaxy, in the halo, like satellites surrounding a great spiral disk. Their spherical shapes and densely packed cores have survived cosmic encounters, tidal forces, and billions of years of galactic evolution. The very fact that they still exist speaks to their resilience. From the standpoint of timekeeping, globular clusters are extraordinary laboratories. Because their stars are coeval, meaning born together, astronomers can place them on the Hertzsprung-Russell diagram and trace their evolutionary stages with unusual clarity. The most telling feature is the turn-off point, where stars leave the main sequence as they exhaust their hydrogen fuel. The position of this turn-off is like the hand of a clock, pointing to the cluster's age. Clusters with brighter, more massive stars at the turn-off are younger. Clusters with fainter, less massive stars at the turn-off are older. The oldest globular clusters have turn-off points so low that their ages approach 13 billion years, only slightly younger than the universe itself. But globular clusters provide more than one method of dating. They also contain white dwarfs, the remnants of stars that have already burned out. White dwarfs cool steadily over time, losing their heat to space. By measuring the faintest white dwarfs in a cluster, astronomers can estimate how long they have been cooling. The faintest ones are the oldest, and their temperatures provide another clock. White dwarf cooling ages have confirmed that the oldest clusters are nearly as old as the universe, forming within the first billion years after the Big Bang. The chemistry of globular clusters also tells a story. Their stars show very low metallicity, consistent with early formation, before the galaxy had been enriched by many generations of supernovae. Some clusters show multiple populations of stars, with slight differences in chemical composition, suggesting that even within these ancient systems, more than one generation may have formed. Still, the overall message is clear. Globular clusters are fossils, preserved from the dawn of the Milky Way. For decades, estimates of cluster ages created tension with cosmology. Early models placed them at 15 or 16 billion years old, seemingly older than the universe. As with the Methuselah star, improvements in stellar physics and distance measurements brought them into harmony. Better opacity data, improved handling of element diffusion, and more accurate parallaxes lowered their ages to about 13 billion years. This consistency was a triumph, showing that the clocks of the stars and the clock of the universe could indeed be reconciled. To stand at the eyepiece of a telescope and look at a globular cluster is to see an ancient memory. Long before the Earth formed, before the Sun itself was born, these clusters were already blazing in the young galaxy. They are relics that have survived cosmic time, and they remain among the most valuable guides to the age of the universe. They are not solitary enigmas like the Methuselah star. They are collective witnesses, vast congregations of suns that confirm with one voice the ancient story of the cosmos. And as astronomers probe them more deeply, they reveal not only ages but also the processes by which galaxies themselves were built. The universe has left us these fossils, shining reminders that time is written not only in the expansion of space, but also in the dense gatherings of stars that orbit our home galaxy. The names of the globular clusters may sound like catalogue numbers, yet each of them carries a story written in the oldest starlight. Among the most famous is Messier 15, a compact cluster in the constellation of Pegasus. Through a large telescope, it appears as a shimmering ball of countless stars, with a dense core that brightens toward the center like the glow of an ember. Messier 15 is among the most metal-poor clusters known, with iron content far lower than that of the Sun, and its turn-off point places its age at around 13 billion years. Another equally ancient system is Messier 92 in Hercules, also metal-poor, and also among the very first stellar congregations to emerge in our galaxy. These two, along with several others, serve as benchmarks in the quest to understand cosmic chronology. Globular clusters are not scattered randomly. They trace the halo of the Milky Way, orbiting far outside the spiral arms, where most of the younger stars reside. Their orbits are elongated and inclined, suggesting that they are survivors from a time before the disk of the galaxy settled into its present form. Some may even have originated in dwarf galaxies that were later swallowed by the Milky Way, bringing their ancient clusters with them. This makes them not only fossils of stars, but also fossils of galactic archaeology, carrying memories of mergers and collisions from billions of years ago. When astronomers first tried to assign precise ages to these clusters in the late 20th century, they often obtained values greater than 14 billion years. The implication was troubling. If the clusters were older than the universe, then either the cosmic microwave background age was wrong, or the models of stellar evolution were incomplete. At that time, cosmology was still debating between younger and older universes depending on the value of the Hubble constant. The apparent contradiction kept both sides cautious. The resolution, as so often, came from better data and improved physics. Distances were refined using space-based parallaxes, which reduced uncertainties in luminosity. Stellar models were updated to include element diffusion, the slow sinking of helium, and heavy elements toward the core over billions of years. This effect makes stars appear slightly younger than models without it. Improved opacity calculations, especially for oxygen and iron, also shifted the models. Together, these refinements reduced cluster ages from more than 14 billion years to about 13 billion. With this revision, the clusters no longer threatened to outlive the universe. Instead, they fell neatly within the timeline set by the cosmic microwave background. White dwarf cooling sequences added further confirmation. By plotting the faintest white dwarfs in a cluster, astronomers could see how long the remnants had been cooling. In Messier 4, for example, white dwarf cooling ages gave results of about 12.5 billion years, in agreement with main sequence turn-off estimates. These independent checks strengthened confidence that the clusters were indeed as old as expected, but not impossibly so. The importance of globular clusters goes beyond numbers. They are natural laboratories for understanding how stars evolve in dense environments. Stellar collisions and interactions are common in their crowded cores, producing exotic objects such as blue stragglers, stars that appear younger and hotter than the rest. These anomalies are not signs of new star formation, but the result of mergers and mass transfer, where one star steals material from another. Even these processes tell us something about time, for they show that the clusters are not static fossils, but living systems that continue to evolve slowly, even after 13 billion years. In their collective voice, the clusters confirm the grand narrative. The universe is 13.8 billion years old. The oldest clusters are about 13 billion. They formed when the cosmos was still in its infancy, less than 1 billion years after the Big Bang. They are, quite literally, the memory of that era, orbiting quietly above and below the galactic disk, reminders that the Milky Way itself was built upon ancient foundations. And yet, as accurate as their ages now appear, astronomers remain cautious. The margin for error is still hundreds of millions of years, and any hidden complexities in stellar physics could shift the numbers again. The lesson of the Methuselah star applies equally to clusters. Precision is everything, and humility is essential. But the convergence of multiple methods gives confidence that the broad picture is correct. The clusters are not older than the universe. They are its children, born in the first chapter of galactic history. In this way, globular clusters serve as cosmic fossils. They're crowded stars, shining with the light of a time so ancient it is almost beyond imagination. They are our clearest window into the early Milky Way, and through them we can trace the universe's story back to its opening moments. The power of globular clusters lies not only in their age but also in their endurance. For more than 13 billion years, they have orbited the Milky Way, surviving the collisions and mergers that shaped our galaxy. Each cluster is like a vault of time, a container holding the memory of the cosmos in the form of ancient stars. To study them is to look back into a past when the universe was still young, when the first galaxies were only beginning to take shape. What makes clusters so valuable is their sheer abundance of witnesses. A single star can mislead if its distance, composition, or internal physics are misunderstood. A cluster of hundreds of thousands of stars, all born together, leaves less room for error. Their combined light, their shared evolutionary path, and their distribution across the Hertzsprung-Russell diagram weave a consistent story. When clusters tell us they are 13 billion years old, the evidence does not rest on one fragile calculation, but on the collective testimony of countless suns. Astronomers treat globular clusters as cosmic fossils, not only because they are ancient, but because they preserve conditions that no longer exist elsewhere. The gas clouds from which they formed were poor in metals, enriched only by the very first generations of supernovae. The stars in the clusters still carry that chemical signature, unaltered, across eons. In some clusters, subtle differences in composition reveal that more than one generation of stars formed, perhaps as early stars, expelled material that later condensed into new ones. These second generations are still more than 12 billion years old, but their presence adds richness to the fossil record, showing that even in the earliest times, star formation was complex. Globular clusters also connect the Milky Way to the larger cosmic story. Some clusters appear to have originated in dwarf galaxies that were later absorbed by our own. Their orbits and chemistry bear the marks of foreign birth. This means the halo of the Milky Way is not purely native, but partly assembled from the remnants of other galaxies. Each cluster is thus not only a record of time, but also a record of galactic archaeology, testifying to the mergers and accretions that built the great spiral we see today. For observers, these clusters are among the most spectacular sights in the sky. To peer at Messier 13 in Hercules or Omega Centauri in the southern hemisphere is to confront a globe of fire, thousands of suns pressed together into a ball so dense that the human eye can barely separate them. But beyond their beauty, they embody a truth that is deeply humbling. They remind us that the universe had already lived through billions of years before our planet was born, and that the stars of the clusters were ancient long before Earth's mountains or oceans existed. The convergence of evidence from globular clusters with that from the cosmic microwave background is one of the great successes of modern astronomy. Where once there was contradiction, now there is harmony. The clusters stand as independent confirmation that the universe is about 13.8 billion years old. They are not older than the cosmos. They are its children, born soon after its birth, still circling faithfully after all this time. Their presence prepares us to ask an even deeper question. If globular clusters, formed within the first billion years, are still with us, what about the very first stars that formed even earlier? The clusters are fossils of the Milky Way's youth, but the universe itself had stars before them. Those primordial suns, known as population 3 stars, were the very first to ignite in the cosmic darkness. Unlike the clusters, they are gone, consumed quickly by their own brilliance. Yet the search for their traces continues, for they hold the key to understanding how light first pierced the void. The clusters, then, are a bridge. They carry us from the paradox of the Methuselah star to the broader story of galactic fossils, and they lead us onward to the earliest chapters of cosmic history, when the first stars ignited in a universe barely emerged from its beginning. These ancient swarms remind us that the cosmos does not forget. Its memory is stored in the stars themselves, waiting for us to decipher it. And now, with the evidence of globular clusters in hand, the narrative turns to the early universe and the birth of the very first generation of stars. In the beginning, the universe was hot, dense, and uniform. For the first few 100,000 years after the Big Bang, matter and light were bound together in a glowing plasma. Atoms could not exist because the searing heat tore electrons away from nuclei. The cosmos was filled with a fog of particles and radiation, opaque to light. Time itself had only just begun, measured from the moment of expansion, yet already the seeds of the future were were being planted in tiny fluctuations of density. Around 380,000 years after the beginning, the universe cooled enough for hydrogen and helium atoms to form. This moment, called recombination, released the cosmic microwave background. Light could now travel freely, carrying with it an image of the infant cosmos. But the universe remained dark, in another sense. There were no stars yet. Hydrogen and helium drifted through space in vast clouds, waiting for gravity to pull them together. This period is sometimes called the Cosmic Dark Ages, a time when the universe was transparent but unlit. Gravity worked slowly but relentlessly. Over tens of millions of years, the small fluctuations in density grew. Regions slightly richer in matter pulled in surrounding gas, forming clumps that would eventually become galaxies. Simulations suggest that the first stars formed about 100 to 200 million years after the Big Bang. Compared with the current age of 13.8 billion years, this was astonishingly early, less than 2% of cosmic history. These first stars are known as Population 3, a label meaning the very first generation. Population 3 stars were unlike any stars that followed, composed only of hydrogen and helium, with no heavier elements to cool the gas. They grew to immense sizes. Without metals to radiate heat away, the gas clouds collapsed into very massive stars, some 100 times the mass of the Sun or more. Their lives were short, burning fiercely for only a few million years before exploding as supernovae or collapsing into black holes. None of them have survived to the present day, but their influence was profound. They forged the first heavy elements beyond helium, seeding the cosmos with carbon, oxygen, iron, and more. They also reionized the universe, breaking apart hydrogen atoms with their intense ultraviolet light, ending the Dark Ages and filling the cosmos with starlight for the first time. Because these stars lived and died so quickly, they are absent from today's sky. What we have instead are their descendants, the Population 2 stars, born from gas already enriched with the ashes of their predecessors. Some of these Population 2 stars are still with us, especially the low-mass ones, and they are among the most ancient objects we can observe. By studying them, we catch indirect glimpses of the conditions in which the very first stars lived. Their chemical patterns, especially their scarcity of metals, carry the fingerprint of the primordial universe. The challenge of astronomy is that direct evidence of Population 3 stars remains elusive. Despite decades of searching, no true example has been found. Telescopes scan the sky for stars with absolutely no metals, but so far every star observed contains at least trace amounts. This is not surprising. Massive stars die quickly, while smaller ones, which could have survived, may never have formed in that first epoch because the physics of gas cooling favored giants. Yet the search continues, because finding even one surviving Population 3 star would open a window into the very first chapter of stellar history. The James Webb Space Telescope has begun to push this frontier by observing galaxies so distant that their light has traveled more than 13 billion years to reach us. In these galaxies, astronomers hope to detect the signatures of Population 3 stars indirectly through the chemical fingerprints they left behind in their explosive deaths. The glow of certain elements, the ratios of carbon to oxygen, the absence of iron, all may point to the influence of the very first generation. In this way, the early universe speaks to us, not through direct survivors, but through echoes. The light of distant galaxies, the chemistry of ancient stars in our own Milky Way, and the patterns etched in the cosmic microwave background all converge to tell the story of the first stars. They were brief, brilliant, and essential. Without them, no later stars would exist, no planets would form, and life would have no raw materials. The universe waited hundreds of millions of years before the first starlight, but when it came, it transformed everything. Darkness ended, structure blossomed, history began in earnest. The cosmos was no longer a uniform sea of hydrogen and helium, but a universe of light, heat, and chemistry. And from these beginnings, the chain of generations unfolded, leading to the ancient stars we see today that stand as relics of that distant epoch. The story of the first stars has always been one of inference and pursuit. We know they must have existed, because without them, the cosmos could never have produced the elements we now see in every star, planet, and living creature. Yet no telescope has ever captured a population 3 star directly. Instead, astronomers trace their existence through the shadows they left behind, the fingerprints of their lives and deaths scattered across the universe. The most powerful of these clues is chemical abundance. Every star carries in its light a record of its composition. When starlight is spread into a spectrum, dark lines appear where atoms absorb specific colors. These absorption lines act as signatures, revealing what elements the star contains and in what proportions. Stars born shortly after the Big Bang contain only traces of metals because they inherited gas enriched by only 1 or 2 generations of supernovae. By contrast, stars like our Sun are rich in metals, born after billions of years of recycling. Thus, by searching for stars with the lowest metallicity, astronomers find those closest in time to the population 3 epoch. Among these survivors are stars in the halo of the Milky Way, with iron abundances tens of thousands of times lower than that of the Sunday. Some contain so little iron that it is almost undetectable. These are the population 2 relics, ancient stars that formed from gas touched only lightly by the explosions of the first generation. Their chemical patterns often reveal unusual features. Some show enormous amounts of carbon compared with iron, a signature thought to come from the peculiar nucleosynthesis of massive primordial stars. Others lack certain heavy elements entirely, hinting at the specific type of supernova that seeded their birth cloud. Each of these stars acts as a messenger, carrying the chemical DNA of the long-vanished population 3 stars. The James Webb Space Telescope has added another layer of evidence by peering into the distant universe. Because light takes time to travel, observing galaxies more than 13 billion light-years away means seeing them as they were less than 1 billion years after the Big Bang. In some of these galaxies, astronomers detect emission lines that suggest the presence of extremely hot, massive stars. While not direct proof, these features align with predictions for population 3 stellar populations. The absence of metals in the gas of these early galaxies strengthens the case. Another clue comes from reionization, the epoch when ultraviolet light from the first stars and galaxies stripped electrons from hydrogen atoms across the cosmos. Observations of distant quasars, whose light passes through intervening gas, show that by about 1 billion years after the Big Bang, the universe was fully reionized. The energy required for this transformation points to vast numbers of massive stars in the early universe, consistent with population 3. Their brilliance lit up the cosmos, ending the Dark Ages and setting the stage for cosmic structure as we know it. Simulations of galaxy formation also reinforce the picture. Computer models that begin with the conditions of the early universe consistently show that primordial gas, lacking metals, collapses into massive clumps that ignite as giant stars. These simulations predict that population 3 stars were common in the first few 100 million years, but soon gave way to population 2 as metals spread and cooling became more efficient. In all of this, we see the same pattern. Direct detection remains elusive, but indirect evidence is overwhelming. Population 3 stars were real, they were massive, and they lived and died quickly. Their remnants are the black holes that may have seeded the growth of galaxies. Their supernovae scattered the first heavy elements. Their radiation ended the Dark Ages. They were the universe's first attempt at complexity, and though none remain, their influence pervades everything we see today. For us, the most accessible messengers of this era are the ancient population 2 stars in our own galaxy. Scattered in the halo and in globular clusters, they are survivors that remember. By decoding their chemistry, astronomers reconstruct the lives of stars that vanished billions of years ago. In their spectra, we see the echoes of the very first explosions, the fingerprints of creation itself. The search for the first stars continues, because even a single surviving population 3 star would be a treasure beyond measure. Yet even if none remain, the evidence left in their descendants is enough to write their story. The cosmos remembers its beginnings, not in photographs, but in starlight, in chemistry, in radiation stretched across time. Thus, the early universe, though distant and hidden, is not silent. It speaks through the relics we can study, guiding us back to the first chapter of cosmic history, Hubi Ark, from Ses at I, at Si, and it reminds us that the ancient stars still shining today are not merely old, they are direct links to the dawn of creation. The pursuit of the first stars leads naturally to the survivors we can still see. Though no true population 3 star has ever been identified, astronomers have uncovered a handful of objects so poor in metals that they appear almost primordial. These stars are not the giants of the first generation, but they are the fragile embers of the generations that followed, born in gas clouds, touched only lightly by the ashes of the very first explosions. In the outer halo of the Milky Way, far from the bright spiral arms, these relics dwell in solitude. They are faint, cool, and long-lived, often with masses less than that of the Sunday. Because of their small size, they have burned their hydrogen so slowly that they remain alive after more than 13 billion years. Their atmospheres preserve the composition of the gas from which they formed, making them time capsules of the early universe. Each spectrum is like a message across eternity. One of the most striking features of these ancient survivors is their scarcity of iron. In some cases, the amount is less than 1/10,000th of the Sun's value. Such stars could only have formed from gas enriched by a single supernova, or perhaps none at all. Yet many of them show enhanced carbon, a clue that the explosions of the first massive stars may have produced unusual yields. These carbon-enhanced metal-poor stars hint at exotic nuclear processes in the earliest epochs, processes that shaped the chemistry of the cosmos long before planets or life existed. The importance of these survivors is that they provide a bridge between the unobservable population 3 stars and the observable universe today. By analyzing their abundances, astronomers can infer the masses of the stars that exploded before them, the energies of their deaths, and the elements they scattered. From these clues, a picture emerges of a universe where massive stars lived briefly, sowed the seeds of complexity, and gave rise to smaller, longer-lived stars that we can still see. The James Webb Space Telescope now extends this pursuit beyond our galaxy. By observing the faint light of galaxies more than 13 billion years away, it allows astronomers to study populations of stars at a time when the universe was only a few 100 million years old. Already hints of unusual chemical signatures have emerged, suggesting that we may soon glimpse the collective impact of population 3 stars on their galaxies. If we cannot find them individually in our own sky, we may detect their fingerprints imprinted on distant light. The timeline is striking. The Big Bang occurred 13.8 billion years ago. Within a few 100,000 years, atoms formed. Within a few 100 million years, the first stars ignited. Within the first billion years, globular clusters and galaxies emerged. And across the following billions of years, smaller stars survived, carrying within them the chemical codes of those earliest times. The story is continuous, a chain of creation, stretching from the moment of expansion to the stars we study today. When we gaze at the ancient stars in the halo of our galaxy, we are not just looking at old suns. We are looking at fossils of the universe's first experiments with light and matter. They are direct descendants of stars that lived and died before the Milky Way itself had fully formed. They remind us that the cosmos is not only vast in space but deep in time, with each point of starlight carrying an echo of beginnings. The early universe and the first stars thus set the stage for everything to come. Their brief lives enriched the cosmos. Their violent deaths seeded the elements, and their faint descendants now guide our understanding of cosmic dawn. The forgotten stars older than galaxies themselves are not older than the universe, but they are close enough to its beginning to carry its memory in their light. And so, from the birth of the first stars, the story continues to the discovery of extremely metal-poor stars, living fossils that survive into the present day, bearing witness to the earliest billion years of cosmic history. Among the most valuable relics of the cosmos are the extremely metal-poor stars, objects so deficient in heavy elements that their very existence speaks of the earliest times. These stars are rare, fragile, and faint, but they are among the closest things we have to direct messengers from the first billion years after the Big Bang. Each of them carries within its atmosphere a chemical record that reaches back to the deaths of the first massive stars, offering clues about what those vanished giants were like and how they seeded the universe with the elements that would make planets and life possible. The term metallicity in astronomy refers to the fraction of a star's matter that is made of elements heavier than helium. Our Sun, born after countless cycles of star formation, contains nearly 2% metals. By contrast, some of the oldest halo stars in the Milky Way contain less than 1/10,000th of that fraction. Such stars could only have formed in environments that were nearly pristine, enriched by perhaps a single supernova from the earliest generation. To find them is to look through a keyhole into the deep past, glimpsing conditions that no longer exist anywhere in the modern universe. One of the most celebrated examples is a star catalogued as SMSS J031300.36-670839.3, discovered with the SkyMapper telescope in Australia. Its spectrum revealed an iron abundance less than 1/10,000,000th that of the Sun, the lowest ever recorded. In practical terms, it is almost devoid of iron, yet it shows large amounts of carbon and magnesium. This peculiar chemistry suggests that it formed from gas enriched by the explosion of a single population 3 star, one that ejected light elements but trapped iron in its collapsing core. In this way, the star is not just old, but uniquely informative, telling a story about the very first supernovae. Another famous ancient star is HATE 1523-0901, found in surveys of the galactic halo. Its spectrum contained measurable amounts of thorium and uranium, rare isotopes, with half-lives comparable to the age of the universe. By comparing their abundances with stable elements like europium, astronomers were able to apply nucleocosmochronology, the radioactive dating technique, directly to the star. The result was an age of about 13.2 billion years, placing it among the oldest known stellar objects. For the first time, radioactive decay measured not rocks on Earth, but the age of a star itself, confirming its status as a living fossil from near the dawn of time. These discoveries demonstrate the richness of information encoded in extremely metal-poor stars. Each chemical anomaly points to a different kind of progenitor. Some stars show excess carbon. Others display unusual ratios of neutron capture elements like strontium and barium. The patterns cannot be explained by modern supernovae alone, but align with theoretical predictions of the first stellar explosions, which may have been asymmetric, faint, or hyperenergetic. By assembling the chemical stories of many such stars, astronomers can reconstruct the diversity of population 3 supernovae and the way they seeded the cosmos with the building blocks of complexity. The rarity of these stars is part of their value. Out of billions of stars in the Milky Way, only a few dozen have metallicities so low that they clearly trace to the earliest epochs. Most stars formed later, from gas already enriched many times over, but the few survivors that remain are resilient witnesses, orbiting far in the halo, untouched by the recycling of the galactic disk. Their continued survival is due to their low mass, which allows them to burn fuel slowly and live for timescales comparable to the age of the universe. In them, we see the universe as it was when it was only a few 100 million years old. We see the ashes of the first giants, the fingerprints of explosions that occurred when galaxies were newborn. These are not theoretical objects. They are real stars, faint but observable with modern telescopes, guiding us back to an era long before the Earth existed. And as astronomers study them in greater detail, they reveal not only the physics of ancient stars, but also the history of our own cosmic origins. For without these first explosions and their chemical legacy, the Sun, the Earth, and life itself would never have come to be. The catalogue of extremely metal-poor stars has grown slowly but steadily, each new discovery adding another fragment to the puzzle of the early universe. These stars are found not in the bright spiral arms where young suns are born, but in the outskirts of the Milky Way halo, in faint dwarf galaxies, and sometimes hidden within globular clusters. They are rare jewels scattered through the galaxy, uncovered only by systematic surveys that sift through millions of stars to find those with the weakest absorption lines of heavy elements. Among the most informative of these relics are the carbon-enhanced metal-poor stars. These objects contain iron at levels thousands of times below that of the Sun, yet they display strong signatures of carbon. The imbalance is striking, and it points to unusual processes in the first supernovae. Theoretical models suggest that massive primordial stars may have exploded in ways that expelled carbon and other light elements, while trapping much of their iron in the collapsing core. If a later generation of stars formed from this enriched gas, they would bear the chemical fingerprint of that event. Carbon-enhanced metal-poor stars are therefore not only old, but also direct markers of the peculiar nucleosynthesis of the universe's first giants. One such star, known as He 0107-5240, was found to have an iron abundance less than 1/200,000th that of the Sun, yet it contained significant amounts of carbon and nitrogen. Its spectrum suggested that it had been seeded by a single population, 3 supernova, making it one of the most pristine records of the earliest stellar deaths. Another, He 1327-2326, showed extreme enrichments in elements produced by neutron capture, such as strontium and barium, indicating a different kind of progenitor explosion. Each discovery broadened the picture of what the first supernovae were like, showing that they were not uniform but diverse in their yields and energies. These chemical detectives allow astronomers to build a genealogy of the cosmos. The oldest stars are like ancestral portraits, telling us who their parents were and how they lived. In their carbon, magnesium, strontium, and uranium lines, we see the traces of nuclear reactions that occurred in the hearts of stars more than 13 billion years ago. Without these surviving witnesses, the early universe would remain a blank chapter. With them, it becomes a story, written in detail, even if some passages are still faint. The study of extremely metal-poor stars has also reshaped ideas about galaxy formation. Observations of ultra-faint dwarf galaxies, tiny companions to the Milky Way, reveal that they contain some of the most metal-poor stars ever seen. These galaxies are thought to be fossils themselves, survivors of the first small systems that merged to build larger galaxies. Their stars confirm that the earliest epochs of star formation occurred not only in the Milky Way's halo, but across a multitude of tiny galaxies. Each one contributed to the chemical enrichment of the cosmos, scattering the products of primordial supernovae into the intergalactic medium. The precision of abundance measurements has advanced dramatically with modern spectrographs. Instruments on the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and other facilities allow astronomers to measure chemical abundances with exquisite detail. Even faint halo stars can now be dissected for their chemical secrets. This precision turns each star into a laboratory of the early universe, far beyond what could ever be recreated on Earth. In the grand narrative, these stars matter because they anchor the lower end of the metallicity scale. Just as tree rings tell of droughts and floods, the elements in these ancient stars tell of explosions and enrichments. Each ratio, each anomaly, is a record of a moment when the universe was young. Together, they sketch a picture of the transition from population 3 to population 2, from the first brief lives of giants to the long endurance of smaller stars. The extremely metal-poor stars are therefore not only relics but guides. They illuminate the path from the first light of the cosmos to the structured galaxies of today. Their rarity makes them precious, and their study continues to reshape our understanding of how the universe evolved in its first billion years. And as the catalogue expands, so too does the richness of the story, pointing us ever closer to a complete understanding of the first generations of stars. The story of the extremely metal-poor stars reaches its climax in the details of their chemistry. Every absorption line in their spectra is a clue, every ratio of elements, a fragment of the earliest cosmic story. When astronomers examine these stars with the most powerful spectrographs, they see abundance patterns that cannot be explained by any ordinary modern star. Instead, they find the fingerprints of the very first supernovae, explosions unlike any that we can study nearby today. Some stars show unusually high levels of magnesium compared with iron, a signature of primordial explosions that ejected light elements but trapped heavy ones. Others reveal enhanced levels of calcium, silicon, or titanium, pointing to different nuclear pathways in their progenitors. Still, others display strong enrichment in elements produced by neutron capture, hinting at the earliest R-process events, where heavy nuclei, like gold and uranium, were forged. No two extremely metal-poor stars are identical. Each one is a fossil record of a specific supernova that occurred more than 13 billion years ago, when galaxies were only just beginning to form. Taken together, these chemical stories confirm that the first stellar deaths were diverse. Some primordial stars exploded violently, spreading elements far and wide. Others collapsed into black holes, swallowing much of their own material and leaving behind a subtler chemical legacy. The surviving metal-poor stars thus provide a catalogue of outcomes, showing how the first cycle of birth and death seeded the cosmos with complexity. Without this cycle, later generations of stars would not have had the elements needed to form planets, oceans, and life. The precision of these measurements has turned astronomy into a kind of forensic science. From the faintest halo stars to the sparse populations of dwarf galaxies, astronomers reconstruct events that happened billions of years before Earth formed. Each star is like a crime scene preserved in starlight, holding evidence of explosions that ended long before our solar system came into being. The patience and care required to tease out these patterns reflects the scale of the mystery being solved. The universe leaves only subtle traces of its earliest chapters, and it is through these traces that the story can be recovered. What emerges is a deep connection between the stars we observe today and the birth of the universe itself. Extremely metal-poor stars are not curiosities. They are anchors for cosmology, because their ages and compositions provide independent confirmation of the timeline set by the cosmic microwave background. Their presence shows that the first stars formed within a few 100 million years of the Big Bang, consistent with simulations and with distant galaxies observed by the James Webb Space Telescope. Their chemistry confirms that the earliest nucleosynthesis produced the elements in ways our theories predicted, strengthening confidence in the models of cosmic evolution. At the same time, these stars remind us how delicate the boundary of knowledge is. A single star with unusual chemistry can challenge assumptions about the first supernovae. A misinterpreted abundance ratio can suggest a contradiction with cosmology. Each discovery demands careful analysis, because the stakes are nothing less than the timeline of the universe. The chapter of extremely metal-poor stars closes with the recognition that they are not merely ancient survivors but living laboratories. They allow us to test nuclear physics under conditions impossible to reproduce on Earth. They allow us to trace the ancestry of galaxies. And they provide yet another clock, one that confirms that the universe is indeed 13.8 billion years old, but filled with stars that remember its earliest billion years. The chemistry of these stars encodes the fingerprints of the earliest universe. And those fingerprints not only tell us where we came from, but also lead us to the next question. How can these stellar ages and chemical clocks be reconciled with the broader age of the cosmos itself? The question of the universe's age is not answered by stars alone. It is a problem that stretches from the smallest nuclear reactions in stellar cores to the largest scales of cosmic expansion. Stars provide clocks that tick according to fusion and decay, but the universe itself has a clock, one that runs with the expansion of space. To reconcile the two is to test whether the laws of nature are truly consistent from the scale of atoms to the scale of galaxies. The first attempts to measure the expansion rate of the cosmos came from Edwin Hubble in the 1920s. By observing the redshifts of galaxies and comparing them to their distances, he discovered that galaxies recede from us, and that the farther away they are, the faster they move. This discovery revealed the universe was expanding. By taking the inverse of the expansion rate, one can estimate the age of the universe, in the sense of how long it has been stretching since the beginning. But Hubble's early measurements placed the universe at only 2 billion years old, younger than the Earth itself. Clearly something was wrong. The problem was measurement error. Distances to galaxies were underestimated, making the expansion rate appear too high and the universe too young. Over the decades, improved observations corrected the error. Cepheid variables, supernovae, and later the cosmic microwave background provided more reliable distance scales. The age of the universe gradually climbed from a few billion years to more than 10, then to nearly 14. Each refinement brought the expansion clock closer to agreement with stellar ages, but tensions never fully vanished. Even today, astronomers debate the precise value of the Hubble constant, the rate at which the universe expands. Two methods dominate the modern debate. One uses the cosmic microwave background, the fossil light released 380,000 years after the Big Bang. By analyzing the ripples and patterns in this light with the Planck satellite, cosmologists infer the composition, geometry, and expansion history of the universe. This method yields a Hubble constant that implies an age of about 13.8 billion years. The other method uses direct observations of nearby galaxies and supernovae, building a distance ladder step by step from parallax to Cepheids to Type Ia supernovae. This local measurement produces a slightly higher expansion rate, implying a younger universe by several 100 million years. The difference is not enormous, but it is persistent, and it has become known as the Hubble tension. The implications are significant. If the cosmic microwave background method is correct, then the stars must fit within 13.8 billion years. If the local ladder is correct, the universe could be closer to 13.3. Either way, the ages of the oldest stars and globular clusters press near the limit, but they remain consistent within uncertainties. The Methuselah star, globular clusters like Messier 15 and Messier 92, and extremely metal-poor halo stars all agree broadly with the Planck value. Yet the tension between methods remains, suggesting either hidden errors in measurement or perhaps new physics beyond the standard model of cosmology. For scientists, this is not a crisis, but an opportunity. Discrepancies drive progress. Just as the paradox of the Methuselah star led to refined stellar models, the Hubble tension forces cosmologists to examine every assumption. Are we correctly modeling the physics of the early universe? Is dark energy truly constant, or could it evolve over time? Could unknown particles, perhaps related to neutrinos, have influenced the expansion history? Each possibility is tested against data, and each new observation narrows the field of answers. What matters most is that the clocks agree within reach. No star is confirmed to be older than the universe. The cosmic microwave background, the expansion of galaxies, and the ages of the oldest stars all point to a cosmos that began about 13.8 billion years ago. The agreement is not perfect, but it is closer than ever before in the history of science. That closeness itself is a triumph, showing that independent methods, built on entirely different physics, converge on the same story. Yet the search for precision continues, because even a difference of a few 100 million years matters when testing the foundations of cosmology. The stars press against the boundary, and the expansion rate presses back. Between them lies the truth, waiting to be revealed with greater clarity. The effort to refine the age of the universe has become one of the central projects of modern cosmology. It is a problem not of order of magnitude guesses, but of small margins, where the difference between 13.3 and 13.8 billion years carries profound implications. To approach such precision, astronomers have built overlapping methods of measurement, each independent yet interdependent, forming a lattice of evidence against which theories are tested. The cosmic microwave background remains the gold standard. Its ripples encode the universe's conditions when it was only 380,000 years old. By analyzing the size of those ripples, cosmologists can determine how matter and energy were distributed and how fast the universe was expanding at that time. The Planck satellite, launched in 2009, measured this relic radiation with unprecedented precision. The data revealed not only the age of the universe, but also its composition: about 5% ordinary matter, 27% dark matter, and 68% dark energy. With these parameters, the models of expansion point to an age of 13.8 billion years. The beauty of this method lies in its independence. The cosmic microwave background comes from the early universe itself, long before stars and galaxies complicated the picture. It provides a clean snapshot, unmarred by the uncertainties of stellar models or the peculiarities of local galaxies. Yet its conclusions depend on assuming that the standard cosmological model is correct, that dark energy behaves like a cosmological constant, and that the universe is spatially flat. If those assumptions are even slightly wrong, the inferred age could shift. The local distance ladder, by contrast, builds its argument from the universe we see today. The foundation begins with parallax, the shift of nearby stars, against the background. As Earth orbits the Sunday, Gaia has refined these measurements to extraordinary accuracy, anchoring the first rung of the ladder. The next step uses Cepheid variable stars, whose pulsations relate directly to their luminosity. By measuring their brightness, astronomers determine distances to nearby galaxies. Beyond that, type Ia supernovae serve as standard candles, exploding with nearly uniform brightness and visible across hundreds of millions of light years. Together, these rungs allow astronomers to measure the expansion rate directly in the modern universe. The local ladder yields a Hubble constant about 9% higher than the cosmic microwave background value. That difference translates to a younger universe, closer to 13.3 billion years. Neither result is sloppy. Both are supported by precise data and careful analysis. The tension between them has persisted despite years of effort, and it now stands as one of the most pressing mysteries in cosmology. Into this debate step the stars themselves. The ages of the oldest stellar populations, from globular clusters to extremely metal-poor halo stars, provide an independent cross-check. If the universe were as young as 13.3 billion years, some of these stars would come uncomfortably close to the limit, pressing against it from below. If the universe is 13.8, the agreement is tighter. Either way, the stars confirm that the answer lies in this narrow range, giving confidence that we are not adrift in speculation, but circling near the truth. The interplay between cosmology and stellar astrophysics is striking. The cosmic microwave background looks back almost to the beginning. The distance ladder looks at galaxies around us today. The stars bridge the gap, their lifetimes stretching across the entire history of the cosmos. By combining these approaches, astronomers triangulate the age of the universe with precision unimaginable a century ago. Still, the tension demands resolution. It could be that hidden biases affect the Cepheid calibrations, or that subtle systematics influence the cosmic microwave background analysis. Or it could be that new physics is required, something beyond the standard cosmological model. In any case, the stars will remain vital referees. Their ages cannot be altered by changing cosmological assumptions. They are what they are, independent witnesses to the universe's timeline. In this way, stellar clocks serve not only as relics of the past, but as arbiters of theory. They force cosmology to remain consistent with the evidence written in starlight. And they remind us that the quest to refine the age of the universe is not just about numbers, but about the harmony of physics across all scales. The pursuit of precision in the age of the universe is a story of narrowing uncertainties. A century ago, the estimates varied so wildly that the Earth itself seemed older than the cosmos. Today, the debate is about a difference of only a few 100 million years. On human scales, that is vast, but on cosmic scales, it is a hair's breadth. This narrowing of the gap is not just a matter of better instruments. It reflects the growing coherence of science, the convergence of independent methods that should have nothing to do with one another, yet arrive at nearly the same answer. When the cosmic microwave background points to 13.8 billion years, when the distance ladder suggests 13.3, and when the stars themselves insist on ages around 13, the message is clear. We are circling the truth. The clocks may not yet strike in perfect unison, but their rhythms are close enough to resonate. Each refinement, each new observation, brings the harmony closer. The importance of this refinement is not only academic. The precise age of the universe is tied to fundamental questions about its contents and its fate. If the universe is younger, then dark energy may be behaving differently than we assume. If it is older, then our models of galaxy formation may need adjustment. In either case, the solution will reveal something about the nature of reality itself. The stakes, are nothing less than the structure of the cosmos. Here the stars provide a sobering reminder. They cannot be fooled by assumptions about dark energy or neutrino physics. Their lifetimes depend only on the physics of fusion and the constants of nature. If their ages press against the cosmic limit, then cosmology must adjust to them. This is why stellar dating has remained central to the debate. It anchors cosmology to the tangible, to the light of real stars, whose lives span billions of years. In recent years, improvements in both stellar modeling and cosmological data have brought the clocks into closer alignment. The Methuselah star, once thought older than the universe, now fits within error bars. Globular clusters, once placed at 16 billion years, are now understood to be around 13. White dwarf cooling sequences, radioactive dating of thorium and uranium, and asteroseismology all converge near the same age. The consistency across these independent methods builds confidence that the universe is not 13 or 20 or 50 billion years old, but about 14, give or take a few hundred million. The remaining tension between the local distance ladder and the cosmic microwave background may yet conceal new physics. But even if it does, the solution will not overthrow the cosmic timeline. It will refine it. The stars, clusters, and cosmic radiation all insist that the universe began in a single event about 13.8 billion years ago. The refinement of this number is not a search for order of magnitude certainty, but for the fine detail that will reveal whether dark energy is constant, whether new particles exist, or whether the geometry of space holds subtle surprises. In this way, the tension between clocks is not a weakness, but a strength. It drives scientists to sharpen their instruments, to reduce every source of error, and to push models to their limits. The more closely the clocks agree, the more confident we can be that our story of the universe is true. The more they disagree, the more opportunities arise to discover something new. The age of the universe is not just a number. It is the framework within which all of cosmic history unfolds. To know it with precision is to know when the first stars ignited, when galaxies formed, and when the seeds of life became possible. It is to anchor ourselves in time as well as in space. And it is to prepare for the next chapter, where the tools of modern astronomy reveal the ancient light with clarity never before possible. The tension between stellar and cosmological clocks drives deeper precision in both, and it sets the stage for the role of modern instruments, which continue to refine our vision of the universe's past and its true age. The progress of cosmic timekeeping has always been tied to the power of instruments. Each leap in technology has sharpened our view of the heavens, transforming faint points of light into sources of knowledge. From the first telescopes that revealed moons around Jupiter to the space-based observatories that now scan the edges of the universe, astronomy advances by extending the reach of human sight. The story of the oldest stars and the refinement of the universe's age is inseparable from the tools we have built to study them. The Hubble Space Telescope was one of the first great leaps into this modern era. Launched in 1990, Hubble rose above Earth's turbulent atmosphere, providing sharp images and precise measurements free from distortion. Among its many achievements was the refinement of parallax, the tiny shift in a star's position as Earth orbits the Sunday. For nearby stars, parallax is the most direct measure of distance, and distance is the foundation for nearly every other stellar property. With Hubble's precision, astronomers were able to determine distances to ancient stars, like HD 1402883, with unprecedented accuracy. That, in turn, allowed them to calculate absolute luminosities and feed them into models of stellar evolution. Without Hubble, the Methuselah paradox might never have been identified, and certainly could not have been resolved with such clarity. Following Hubble came Gaia, the European Space Agency's mission dedicated entirely to astrometry, the precise measurement of stellar positions and motions. Launched in 2013, Gaia has mapped the locations and velocities of more than 1 billion stars in the Milky Way. Its accuracy in measuring parallax surpasses Hubble by orders of magnitude. For the oldest stars, this means distances are no longer rough estimates, but precise values with tiny margins of error. The ripple effects are enormous. Luminosities are known more reliably. Ages derived from stellar models are more secure. The catalogue of extremely metal-poor stars is anchored in solid distance data rather than uncertain guesses. Gaia has become the cornerstone of modern stellar archaeology. Spectroscopy has also advanced in tandem. Instruments on the Very Large Telescope in Chile and the Keck Observatory in Hawaii can split starlight into fine detail, revealing the faintest traces of elements like uranium and thorium. These delicate measurements allow radioactive dating of stars, such as HE 1523-0901, providing ages derived not from models, but from the decay of nuclei. The ability to detect such faint absorption lines requires stability, resolution, and patience. Modern spectrographs achieve all three, turning the atmospheres of ancient stars into cosmic clocks that tick with billion-year hands. At the same time, space missions like Kepler and TESS have opened the window of asteroseismology. By recording tiny fluctuations in stellar brightness, they allow astronomers to hear the oscillations of stars. These oscillations reveal the density structure of stellar interiors, providing another measure of age independent of chemical abundances. Where once the ages of stars were inferred from their positions on diagrams, now they can be read from the vibrations of their surfaces. This is the difference between estimating a heart's health from an X-ray and listening to its pulse directly. Each of these instruments adds precision, but together they form a symphony. Distances from Gaia, spectra from ground-based telescopes, oscillations from Kepler and TESS, and cosmological data from Planck and the James Webb Space Telescope converge to tell a story with unprecedented clarity. The uncertainties that once left stars older than the universe are narrowing. The clocks are not perfect, but they are becoming synchronized. And the process is not finished. With every new generation of instruments, the story of cosmic time grows sharper. The oldest stars no longer appear as vague relics. They become precise markers of the universe's timeline, their ages cross-checked and confirmed by multiple independent methods. Modern astronomy has transformed them from curiosities into chronometers, and in doing so, has brought the cosmos itself into sharper focus. The forgotten stars are no longer forgotten. They are measured, catalogued, and studied with tools of extraordinary sophistication, and through them, we measure not only their lifetimes, but the lifetime of the universe itself. The power of modern instruments lies not only in their precision, but in the new dimensions they open. Spectroscopy, for example, has become the language through which ancient stars tell their stories. When light from a star is spread into a spectrum, each element imprints a set of lines, faint but distinct. For extremely metal-poor stars, these lines are almost ghostly, yet with today's spectrographs, they can be measured with astonishing accuracy. This allows astronomers to detect not only iron, carbon, and magnesium, but also rarer elements such as europium, thorium, and uranium. From these faint traces, entire histories are reconstructed. Without such instruments, the secrets of the oldest stars would remain locked in silence. Asteroseismology represents another revolution. Missions like Kepler and TESS were designed primarily to detect exoplanets, but they also revealed the tiny pulsations of stars. These oscillations arise because sound waves bounce within a star, causing its surface to tremble. The frequencies of these vibrations depend on the density and structure of the stellar interior. By decoding the oscillation spectrum, astronomers can determine the age of a star with remarkable precision, often to within a few percent. This method is especially powerful because it bypasses many uncertainties of traditional models. Instead of inferring age indirectly, it reads it directly from the star's pulse. For ancient stars near the cosmic age limit, this precision is invaluable. And then there is the James Webb Space Telescope, launched to look deeper into time than any instrument before. With its infrared vision, Webb can see galaxies so distant that their light has been stretched by cosmic expansion for more than 13 billion years. In those faint smudges of light lie the clues to when the first stars and clusters formed. Already, Webb has revealed galaxies existing only a few 100 million years after the Big Bang, pushing the frontier of observation to within the first 5% of cosmic history. These discoveries are forcing theorists to refine their models of galaxy formation, and they may soon provide indirect evidence of the first population, 3 stars, through the chemical fingerprints imprinted on early galaxies. The synergy of these instruments is what makes them powerful. Gaia provides distances, ensuring that luminosities are accurate. Ground-based spectrographs decode chemical abundances, revealing the fingerprints of ancient nucleosynthesis. Astroseismology measures the vibrations of stars, offering direct age estimates. Webb peers into the past, showing when the first galaxies and clusters assembled. Together, they create a cross-checked, multi-layered chronometer that stretches from the present back to the first billion years. It is easy to forget how fragile these achievements are. A star's spectrum is only a faint trickle of photons, often billions of years old, spread across space to reach our telescopes. The signal can be drowned by noise, blurred by Earth's atmosphere, or hidden by interstellar dust. Yet with technology that isolates, amplifies, and stabilizes light, astronomers can read from those photons the story of nuclear reactions, explosions, and cosmic history. The triumph is not only in the scale of what is observed, but in the delicacy of the tools that make the observations possible. Every new advance sharpens the picture. Where once the Methuselah star threatened to upend cosmology, Gaia and modern spectroscopy brought it into harmony. Where once the ages of globular clusters seemed older than the universe, white dwarf cooling sequences confirmed their consistency. Where once the first stars seemed forever beyond our reach, Webb has opened a path to their indirect signatures. Modern instruments are not simply tools, they are bridges across time, carrying us to the edges of cosmic history. And as they work in concert, they reveal the universe not as a puzzle of contradictions, but as a coherent story whose details are finally coming into focus. Each new generation of instruments has not only clarified old mysteries but also prepared us for the next frontier. The refinement of stellar ages is not an endpoint, but a continuous process where every improvement in technology shrinks uncertainties and pushes the boundary of the knowable further back in time. Just as Hubble revealed details invisible from Earth, and Gaia mapped the Milky Way with unprecedented precision, future instruments will probe even deeper, unlocking stories still hidden in the faintest starlight. The James Webb Space Telescope has already shown what such a leap can achieve. Its ability to detect galaxies that existed only a few 100 million years after the Big Bang has challenged models of how quickly structures could form. If galaxies that massive were already present so early, it means star formation was vigorous in the universe's infancy. This realization has driven theorists to refine simulations, reconsidering the physics of cooling, feedback, and early black hole growth. Webb's discoveries hint that the story of the first stars may be richer and more complex than once imagined, and they point the way to still greater questions. On the ground, new telescopes are rising that will push spectroscopy to levels never before possible. The extremely large telescope in Chile, with a primary mirror more than 30 meters wide, will gather enough light to analyze faint stars in distant galaxies, tracing their chemical compositions in exquisite detail. The 30-meter telescope and the giant Magellan telescope will join this effort, creating a fleet of instruments capable of dissecting starlight across the universe. These observatories will not only refine the abundances of known extremely metal-poor stars, but also extend the search for even rarer survivors, perhaps revealing stars that preserve an even more pristine record of the early cosmos. Radio astronomy also contributes to this story. The square-kilometer array, now under construction, will map the hydrogen distribution of the early universe, showing how the first stars reionized the cosmos. By tracing the faint glow of neutral hydrogen across billions of years, it will provide a complementary chronometer, revealing the timeline of cosmic dawn with new clarity. Together with optical and infrared instruments, radio telescopes will create a multi-wavelength portrait of the earliest epochs, weaving different forms of light into a coherent narrative of time. The importance of these advances cannot be overstated. Each star, each cluster, each galaxy must be measured with precision if the clocks of the cosmos are to remain synchronized. A discrepancy of even a few 100 million years could signal new physics, perhaps in the behavior of dark energy, or in the properties of particles we have not yet discovered. Precision in cosmic time is not a matter of trivia. It is a doorway to fundamental truths about reality itself. The forgotten stars, once obscure points in the halo of the Milky Way, are now at the center of this pursuit. With modern instruments, they are no longer silent witnesses, but eloquent narrators, speaking in the language of spectra, oscillations, and precise motions. Each photon they emit becomes part of the evidence, each observation another refinement of the cosmic timeline. As we look ahead, it is clear that the quest will continue. New missions, more powerful telescopes, and ever sharper instruments will push our reach closer to the beginning. The stars that seem to defy the age of the universe will be understood with clarity, and the harmony between stellar clocks and cosmic expansion will be tested at ever higher precision. The role of modern instruments, then, is not only to solve old puzzles, but to prepare us for new ones. They sharpen our sight, extend our reach, and remind us that the universe always has more to reveal. With each leap in technology, the cosmic story grows richer, more detailed, and more profound. Each technological advance sharpens the picture of stellar antiquity, and it is this relentless pursuit of clarity that ensures the clocks of the cosmos continue to converge, guiding us closer to the truth of the universe's age. The effort to measure the ages of stars and the universe itself is a triumph of science, but it is also a story marked by uncertainties, revisions, and debates. At the heart of the challenge lies the extraordinary sensitivity of these calculations. A single assumption about how atoms absorb light, a slight revision to a nuclear reaction rate, or a minor change in the estimated distance to a star can shift its calculated age by hundreds of millions of years. When the goal is to align stellar lifetimes with the 13.8 billion years of the universe, such differences become crucial. One source of uncertainty is the physics of stellar interiors. Stars are not transparent spheres. Energy generated in their cores must travel outward through layers of gas, sometimes radiating, sometimes carried by convection. The rate at which energy escapes depends on how photons interact with atoms, a property known as opacity. For decades, opacity tables used in stellar models were incomplete, lacking precise data for many elements at the temperatures and pressures found in stars. When improved opacity data became available, the calculated lifetimes of stars changed, altering their inferred ages. This was one reason globular clusters, once thought older than the universe, were reassigned to more consistent ages. Another challenge comes from element diffusion. Over billions of years, heavier elements like helium and iron slowly sink toward the centers of stars, leaving their surfaces depleted. If models neglect this process, they misrepresent the star's composition and brightness, leading to errors in age estimates. Including diffusion makes stars appear slightly younger, helping to reconcile them with the age of the universe. Yet, the efficiency of this process is not fully known, and different assumptions yield different results. Distance measurements have also been a perennial source of uncertainty. Luminosity is central to determining age, but luminosity can only be known if distance is measured accurately. Before space-based parallaxes, distances to ancient stars were uncertain by tens of percent. That uncertainty propagated into stellar ages, sometimes pushing them beyond the cosmic limit. Missions like Hubble and Gaia have dramatically improved this, but even Gaia's exquisite precision is not immune to systematic errors, which must be carefully accounted for. The nuclear reaction rates that govern fusion in stellar cores add another layer of uncertainty. The rate at which protons fuse into helium, or at which helium fuses into carbon and oxygen, determines how quickly a star consumes its fuel. These reactions are measured in laboratories on Earth, but at energies far higher than those in stellar interiors. Extrapolating those rates down to stellar conditions involves uncertainties. Even small changes alter the calculated lifetimes of stars, shifting their inferred ages. Because of these factors, debates have flourished. For some, the apparent paradox of stars older than the universe suggested that cosmology itself might be flawed. Perhaps the expansion rate was mismeasured, or dark energy behaved differently than assumed. For others, The more likely explanation was in the details of stellar physics. Over time, refinements in models have favored the latter view. Stars that once appeared older than the universe now fit within the cosmic age, but the memory of the paradox lingers as a reminder to remain cautious. The Hubble tension has added fresh fuel to the debate. If the universe is 13.3 billion years old, as suggested by local distance ladder measurements, then the oldest stars must fit within that limit. If it is 13.8 billion years, as the cosmic microwave background indicates, then the stars fit more comfortably. Either way, the debate pushes scientists to refine their tools. The stars do not change, but our interpretations of them do, and each new observation forces a reassessment of assumptions. What emerges is not a picture of failure, but of progress. Disagreements in science are not signs of weakness. They are the engines of discovery. The Methuselah star, globular clusters, and the Hubble tension have all served as catalysts, compelling astronomers to test and retest their models. In doing so, they have built confidence that the broad picture is correct, even as they chase the fine details. The paradoxes remind us that knowledge is fragile at the edges. The closer we come to precision, the more important every detail becomes. In the debate over stellar and cosmic ages, the differences are no longer billions of years, but mere fractions of the universe's lifetime. Yet within those fractions may lie the keys to new physics, waiting to be uncovered. The debates over stellar and cosmic ages have often been framed in dramatic terms. Headlines spoke of an age crisis when the Methuselah star appeared older than the universe, or when globular clusters seemed to defy the cosmic clock. Yet within the scientific community, the tone was more measured. Most astronomers suspected that the paradoxes arose not from fundamental errors in cosmology, but from the uncertainties of stellar models and observations. Even so, the discussions were intense, because if the paradoxes could not be resolved, they would demand a radical rethink of physics itself. One line of debate centered on stellar opacities. For decades, the data tables that governed how light interacts with atoms in stellar interiors were incomplete. When new experiments and calculations improved these tables, the resulting models produced stars that evolved slightly differently. Ages shifted downward by hundreds of millions of years, resolving many contradictions. Some argued that this demonstrated how fragile stellar dating could be, dependent on details invisible to direct observation. Others countered that this was precisely how science should work. As data improved, models adapted, and apparent paradoxes dissolved. Another debate focused on the mixing of elements in stars. Convection zones, where hot material rises and cooler material sinks, are notoriously difficult to model. The efficiency of this mixing affects the transport of energy and the distribution of elements. Different assumptions about mixing lengths and turbulence produce different evolutionary tracks, leading to divergent age estimates. Critics of stellar dating argued that until such processes were better understood, claims of stars older than 13 billion years should be treated with caution. Defenders replied that by comparing many stars and clusters, the uncertainties could be averaged out, yielding reliable results despite the complexities. Systematic errors in distance measurement also became a battleground. Before Gaia, distances to ancient stars relied on indirect methods that carried significant uncertainties. Some astronomers argued that these errors explained the paradoxes, while others maintained that even with uncertainties, the ages seemed uncomfortably high. Gaia's release of precise parallaxes silenced much of this debate by providing distances so accurate that luminosities and ages could no longer be dismissed as products of poor measurement. The Methuselah star's revised age after Gaia was a striking demonstration of how one instrument could transform a controversy. The larger cosmological debate, however, remains alive in the Hubble tension. Here the disagreement is not about stars, but about the expansion rate of the universe. Some scientists argue that the local distance ladder is affected by hidden biases, perhaps in the calibration of Cepheid variables, or the treatment of supernovae. Others insist the measurements are robust and that the tension points to new physics, such as evolving dark energy or extra neutrino species. Stellar ages play a quiet but important role in this debate, acting as a sanity check. If local measurements implied a universe younger than 13 billion years, stars older than that would quickly expose the inconsistency. So far, the overlap remains, keeping both sides grounded. Was there ever truly an age crisis? With hindsight, many astronomers say no. The paradoxes arose from uncertainties, not contradictions. The Methuselah star was never really older than the universe. Globular clusters were never truly 16 billion years old. The crises were products of incomplete knowledge, resolved by better data. Yet, the perception of a crisis served a purpose. It motivated intense research, new instruments, and careful reanalysis. Without the specter of paradox, the drive for precision might have been slower. Science often advances in this way, propelled by apparent contradictions that turn out to be illusions once the data improve. The history of stellar ages is full of such episodes, each one strengthening the field rather than weakening it. The debates may have seemed contentious, but they were the lifeblood of progress. Today, the consensus is clear. No star has been proven older than the universe. The clocks are not perfect, but they converge within the narrow limits set by cosmology. What remains is not crisis, but opportunity, the chance to refine our understanding until even the smallest discrepancies yield their secrets. Science thrives on questions that press against its boundaries, and the debates about stellar and cosmic ages are examples of this process at its best. The disagreements were never merely about numbers. They were about the integrity of our models, the reliability of our instruments, and the possibility that nature might be more complex than we imagine. Each time a star appeared to threaten the cosmic timeline, it became a test of whether science could adapt and refine itself in the face of uncertainty. What makes these debates valuable is that they forced precision. If the Methuselah star had neatly fit within expectations from the beginning, there might have been less urgency to improve opacity data, refine nuclear reaction rates, or launch missions like Gaia. If globular clusters had always been placed at 13 billion years, the field might have moved more slowly toward the precision we now enjoy. The very appearance of contradiction was what fueled progress. It sharpened the questions, rallied new observations, and produced deeper consistency. Yet uncertainty persists, and perhaps always will. Stars are complex, dynamic systems, not perfect spheres of gas, evolving in ideal conditions. Their mixing, rotation, magnetic fields, and interactions with companions all affect their evolution in ways not fully captured by models. The expansion of the universe, though broadly understood, still depends on parameters like dark energy and dark matter that remain mysterious in essence. No matter how fine our measurements become, margins of error will remain, and debates will continue. This is not a weakness of science, but its natural state. The near equality of stellar and cosmic ages is, in itself, scientifically profound. That stars, clusters, radioactive isotopes, and the cosmic microwave background all converge on roughly 13 to 14 billion years is a testament to the coherence of the universe. The clocks are built on entirely different physics: fusion, radioactive decay, oscillations, expansion of space, and the relic radiation of the Big Bang. That they agree within a few percent is not coincidence. It is evidence that our understanding of nature rests on solid foundations. At the same time, the closeness of the match means that even small discrepancies matter. If the oldest stars were found to be hundreds of millions of years younger than the universe, it would be reassuring, but unremarkable. The fact that they press so closely against the limit is what makes them powerful tests of cosmology. They tell us not only that our broad picture is correct, but also that our pursuit of fine detail is justified. The universe is not sloppy with its truths. It hides them in the smallest margins, where only the sharpest instruments and most careful models can reach. Thus, the so-called crises of stellar ages are better understood as catalysts. They were sparks that illuminated the path forward, reminders that progress is born, not from easy answers, but from tension between observation and theory. The Methuselah star, the ancient clusters, and the Hubble tension are chapters in this larger story, each one showing how science grows stronger by wrestling with uncertainty. In the end, The debates teach us humility and perseverance. The universe is vast in time and space, yet it allows us to measure its age with extraordinary precision. The stars may not be older than the cosmos, but they stand close enough to its beginning to keep us honest, to remind us that every margin of error carries meaning, and that the pursuit of truth is endless. And so the paradox may be less about stars being too old, and more about how close our measurements must get to truth. The forgotten stars teach us not to fear contradiction, but to embrace it as the engine of discovery. The story of the universe is written not only in galaxies and cosmic radiation, but also in the quiet light of its oldest stars. These forgotten stars, faint and unassuming in the halo of the Milky Way, or hidden in globular clusters, carry lessons that reach far beyond their own existence. They are not merely ancient, they are teachers, laboratories, and guides to truths about physics and cosmology that cannot be learned in any other way. To study them is to glimpse the laws of nature at work across billions of years, to test whether our understanding holds steady from the smallest nuclei to the largest scales of space. One of their greatest lessons is humility. Time and again, stars have appeared to defy our expectations. The Methuselah star seemed older than the universe until our instruments and models improved. Globular clusters once appeared to outdate the cosmos itself until opacity and diffusion were properly accounted for. Extremely metal-poor stars, with their strange chemistry, revealed nuclear processes in the earliest supernovae that no laboratory on Earth could have predicted. In each case, the contradiction was not a failure, but an invitation. It forced us to refine, to question, and to improve. Science grew stronger because the stars demanded it. They also teach us about the unity of physics. The fact that radioactive decay in a star's atmosphere, hydrogen fusion in its core, oscillations in its surface, and the expansion of the universe all converge on the same timescale is extraordinary. It shows that the laws of nature are not fragmented but coherent across scales and epochs. The same constants that govern a nuclear reaction in a terrestrial laboratory govern the lifetimes of stars across billions of years. The same equations that describe photons bouncing in a plasma 380,000 years after the Big Bang also describe the cosmic microwave background we observe today. The agreement of these independent clocks is a profound confirmation that the universe is comprehensible. Another lesson lies in the chemistry of the oldest stars. Their atmospheres are archives of creation, preserving the ashes of the first stellar generations. From them, we have learned how the first supernovae scattered carbon, oxygen, and iron. From them, we have seen evidence for the R process, which forged the heavy elements like gold and uranium. Without these ancient survivors, we would know far less about how the cosmos transitioned from a simple soup of hydrogen and helium to the rich periodic table on which life depends. The stars are not passive relics. They are active participants in the telling of history. Perhaps most of all, they remind us of continuity. The light of the oldest stars has been shining since long before the Earth formed, and it will continue long after our world is gone. Their lifetimes span nearly the entire history of the cosmos. To study them is to connect with a timescale that dwarfs human history, to see ourselves as part of a much larger story. The universe did not begin with us, nor will it end with us, but in the patient light of ancient stars, we find our place. The forgotten stars are not older than the universe, but they are old enough to touch its beginning. They carry its memory in their light, and they share it freely with anyone who takes the time to look. In their quiet endurance lies a lesson in perspective, that truth is found not in certainty, but in refinement, not in perfection, but in the pursuit of harmony between theory and observation. And in this way, the ancient stars teach us not only about the universe, but about ourselves, about the persistence and humility required to understand reality. The ancient stars do more than preserve memory. They serve as natural laboratories, places where the laws of physics can be tested under conditions impossible to recreate on Earth. Inside their cores, hydrogen fuses into helium at pressures and temperatures that dwarf anything achievable in a reactor. In their atmospheres, atoms absorb light at energies that probe the structure of matter with exquisite sensitivity. By observing these processes across billions of years, astronomers can confirm that the fundamental constants of nature remain unchanged. If the rate of fusion or the decay of uranium had shifted even slightly over cosmic history, the ages of stars would not align with the age of the universe. The harmony we see is not only reassuring, it is evidence that the laws of physics are stable across time and space. These stars also anchor the cosmic timeline. They are fixed points against which theories must be measured. When cosmology suggests a universe of 13.8 billion years, the stars must not outlive it. When stellar physics implies ages approaching that limit, cosmology must remain consistent. The clocks of the stars and the clock of the cosmos are independent, yet intertwined. Each checks the other, ensuring that neither drifts into speculation. In this way, the stars act as guardians of truth, keeping cosmology tethered to observation. The importance of this anchoring role extends beyond age alone. The chemical patterns in extremely metal-poor stars reveal not just when, but how the universe evolved. They confirm that the first heavy elements were forged in massive stars and scattered by supernovae. They show that our process nucleosynthesis, responsible for elements like platinum and uranium, occurred in the earliest times. They reveal that galaxies were enriched unevenly, with different supernovae leaving different fingerprints. These insights are not merely about the past. They shape our understanding of galaxy formation, dark matter distribution, and even the conditions for habitable planets. In studying these stars, astronomers also test the edges of theory. If a star were ever found with no metals at all, it might be a surviving population 3 star, a discovery that would revolutionize astrophysics. If a star were found to be significantly older than the universe, it would demand new physics entirely. Even though no such star has yet been confirmed, the search itself keeps science honest, forcing every measurement and every assumption to be tested against reality. The stars are not only objects of study but also challenges, constantly pressing against the limits of what we know. They also illuminate the future of cosmology. As instruments grow sharper, the precision of stellar ages will improve, narrowing uncertainties from hundreds of millions of years to tens. New telescopes will probe deeper into the halos of galaxies, uncovering even rarer and more primitive stars. The James Webb Space Telescope and its successors will reveal the chemical fingerprints of population 3 stars in distant galaxies. Each step forward will tie the stars more tightly to the cosmic story, confirming or challenging the models that describe the universe's birth and growth. For humanity, these ancient stars carry a different lesson. They remind us that our place in the cosmos is small in scale, but vast in connection. The calcium in our bones and the iron in our blood were forged in stars like these, billions of years before Earth existed. To look at an extremely metal-poor star is to see, in real time, the origins of our own matter. We are not separate from cosmic history, but products of it, linked directly to the light that still shines from the oldest suns. The forgotten stars may not speak in words, but their light tells us everything we need to know. They are not mysteries meant to unsettle us, but guides meant to teach us. And as we refine our instruments and models, they will continue to instruct us, showing that the quest for truth is not finished, but ongoing. The final lesson of the ancient stars is perspective. In their light, we see not only the past of the cosmos, but also the future of our search for knowledge. They show us that the universe is comprehensible, that its clocks can be read, and that its story can be told with coherence across billions of years. At the same time, they remind us that certainty is always provisional, that every answer carries within it the seed of new questions. To stand beneath a sky filled with starlight is to stand at the boundary between what we know and what we still seek. The forgotten stars are not older than the universe, but they exist at its edge, so close to the beginning that their lives stretch almost the entire length of cosmic time. They are not paradoxes to be feared, but treasures to be cherished, because they confirm that the universe does not lie to us. Its clocks agree, even when we must work tirelessly to hear them strike in unison. In their near equality, we find confidence that the framework of cosmology is strong. There is poetry in their endurance. A star like HD 140283 has shone through every chapter of the Milky Way's history. It burned before our sun was born, before the Earth formed, before life stirred in the oceans, and before humans looked upward and wondered. Globular clusters have circled the galaxy since its infancy, carrying the memory of its birth. Extremely metal-poor stars hold within them the ashes of the first giants, atoms forged when the cosmos was still in its youth. These are not abstractions. They are real stars, visible through telescopes, present in the night sky, whispering their story through faint but steady light. To listen to them is to hear the universe speak. They tell us that the cosmos has a beginning, that it is finite in age, and that its story is written not only in distant radiation, but in the very stars that surround us. They show us that science is not the conquest of certainty, but the pursuit of harmony, the alignment of theory with observation, until both sing in tune. In the end, what ancient stars teach us is more than physics. They teach us patience, humility, and wonder. They remind us that truth emerges slowly, through careful refinement, through contradiction, embraced rather than denied. They remind us that we are part of a universe vast in time yet connected through light that travels across ages to reach us. The forgotten stars are not forgotten at all. They stand at the threshold of creation, carrying the memory of beginnings in their light. And as long as they shine, they will continue to tell us who we are, where we came from, and how the universe itself came to be.